Hello and welcome to the Grand Haven Musical Fountain new feature nicknamed The Doves. The scope of this project was to concept, design, prototype, and build a new water feature for the Grand Haven Musical Fountain to add on an 11th feature to the already existing 10 features, which are the bazookas, the rings, the sweeps, the peacock, helix, wave, voice spout, candelabra, front curtain, and the ring center spouts. Since we were also tasked with creating the water stream aesthetic as well as making the feature, we started looking at other fountains in order to get a concept that we all liked. And eventually we landed on the dovetails, as we call them, or the doves for short, as they still have a rotation element which complements the helix recent addition feature, but it also has a water stream similar to the peacock, the first major addition to the fountain, as we honor the fountain's 60th anniversary with this unveiling. The environment that this project exists in is chlorinated water and Michigan winter, so early on in the project we decided to use all stainless steel or galvanized steel for our build. And now we will move on to the project specifications for the new feature. Starting with, the water feature must have a minimum height of 15 feet while in use. Also, the water feature nozzle outlet must be at least a 1/4 inch in diameter. The water feature must be able to be winterized. It must have minimal maintenance. The water feature must be able to withstand at least 150 psi of water pressure, as that is the max that can go through the fountain. The water feature must be aesthetically pleasing, as voted on by the committee. And then it also needs to have a panel view alarm history page, which is used for the software side of the feature. After choosing the doves as our aesthetic for the water stream, we had to think about how to design the feature housing, where the water would go through, and the structure to support it. So we broke that down into 3 critical subfunctions, which were the water stream that the audience will see, the area for self-propulsion, and then the structure that will support the tall extrusion of the pipe and also the catching of the arms, since this feature needs to also be able to be run stopped. Going deeper into the first critical subfunction of the cap where the water will be coming out of, we had a few designs, namely the question mark design, the truncated pyramid design, and eventually what we used, the cap design. And the cap design has a steel lug inside of it that helps distribute water a lot more evenly. We saw this in CFD analysis, that the velocity streams in the nozzles were a lot more even. The next critical subfunction to tackle was the propulsion method for giving the feature its rotation, and based on our constraint that it had to be self-propelling, it was really simple to get that critical subfunction fixed, as having arms swept out that were perpendicular to the center pipe that rotated the feature. Once water pressure was applied to the top of the feature, it rotated it as well. The final critical subfunction that was identified was the structure of the base. And what this does is it serves 2 purposes. It supports the center 4-inch steel piping, which has a vertical section of over 50 inches off the ground, and it helps prevent rotation or vibration of that pipe. And it also holds the catch and is able to withstand the forces that are applied to that catch in order to stop the feature, as this feature can be used both in a stationary or rotational method. This structure did undergo a design change. Initially it used outrunners and a lot of 90-degree angles, but instead it has been redesigned now to have an integrated angle that will help withstand the force that is applied to it. This also serves a purpose, as you can see with the rungs that lead up, as a ladder for the fountain repairing or maintenance. Can use that to get up to the top of the feature, and they are then able to remove the feature or do the work that needs to be done on it. As far as the manufacture of the parts, a lot of the more plate parts, such as the feet for attaching the structure to the cement or the concrete, Those were plasma cut, as well as the cradles, as were previously seen. The rest of the raw stock, it's all stainless steel. It was used on the well saw to be cut down and then milled flat. And then it was handed off to a professional welder, as stainless steel is a very hard material to weld. We had a professional take care of that for us for the actual assembly of the cap to the piping, and then as well as the entire structure. Some of the more miscellaneous parts, such as the Delrin washers that fit inside of the bearing in the middle that allows the rotation, were manufactured using CNC milling. With everything now constructed and assembled, we then put the feature on the fountain, and here's footage of the first time we fired it up during the day.
What way to change? Tell Fred to go. Fred. Woo! Oh, let's go.
This clip was when the pressure was at the highest that it would be at, and you can see a lot of turbulent flow. So what we did, and also to increase the height, what we did was we bored out the bottom of the steel lug more, and that gave the ability for more water to go through, and that really fixed the stream profile. And here is footage of it rotating. This is one of the first times that we had installed everything together, and you can see this cylinder coming up, and that is the cradle, as we call it, catching the arms that are being propelled with the feature on. With all of that testing out of the way during the day, we were then able to install the light fixture, and then here is footage of the first time it's turning on with the lights. As can be seen in that footage, the one especially on the right, the Dove, is moving quite fast rotationally, which is not what we had intended. And this leads me into one of our biggest problems, was actually getting that speed to be consistent. The main reason for this was the nozzles and the ball valves that we're using to control the rotational speed. Adjusting those is a very fine process, as they are not linearly changing. It is exponentially changing, or squared changing, parabolically changing. So that was one of our biggest problems once we got everything built and installed, was fine-tuning that speed. And that trouble with fine-tuning the speed wasn't only the one feature to our target RPM, it was also getting the two features to be synchronized with each other, as they have different distances from the pump house to the feature locations, which means that they weren't at the same spots as far as where the ball valves were. Overall, it was a very interesting project to work for. There were a lot of moving parts that needed a lot of corrosive resistance material, and handling that isn't always the most straightforward thing. But in the end, we all had a good time, and we hope that you're able to come to the official unveiling August 27th.